My name is Michael McClellan, and I'm with L3 Levine Electronics and Electrics. And a couple things to note before I introduce Joe. This is the GoToWebinar platform, so your phones are muted. We can't hear you, but we want to interact with you. So there is a question box, which many of you have found on the right-hand side. There's a little toolbox where you can ask a question, you can raise your hand, you can, and there will be a few polls during the presentation where you can vote yes or no, or 1 through 5, and tell us how we did. So with that, I'm going to, you also should have a certificate emailed to you automatically no later than 4 p.m. tomorrow if you attended the webinar. And if you don't get that by 4 p.m. tomorrow, then please call or email L3 and we'll get that to you.
All righty. Thanks to obviously the L3 guys for setting this up, and specifically to Michael and John. My name is Joe Campa. I am the regional sales manager for the Southeast for post-Glover resistors. So we've been in business for a long time, so probably some of you may know me, but mostly most of you guys might at least recognize the post-Glover resistor name. Our presentation today, again, is on dynamic braking. And just a quick background on post-Glover resistors. Again, we've been in business a long time, since 1892. And pretty much what we are is we are a fabrication job shop. And the ironic thing about being a fabrication job shop is we only have one product that we fabricate, and that is resistors. And we make them on site. We have engineering, probably a little over between 13 and 15 engineers out of 125 people, about 125 people. And there's a lot of engineering that goes into doing what we do. We are a 9001 ISO company, and we can sell a lot of different styles of products that come into play from different requirements like CSA and UL and seismic and different environmental atmospheres that come into play for us. As you see, we're located just outside of Cincinnati, Ohio. We're across the river from Cincinnati in Erlanger, Kentucky, which is right near the, if you've ever flown to Cincinnati, we are about probably a good 3 wood away from the airport. If you hit from the airport to our property, we're just right next door. So what we do, again, I'm presenting today is dynamic braking resistors, but we also do neutral grounding, motor control, filter resistors, transit resistors. Basically, all that does is spell out what the application is. So if you open up the box, resistors are resistors. These are just describing what the resistors are going to be used for. So a quick primer for the dynamic braking resistors that we're going to talk about. The main thing is we're going to talk about how we get to the end, which is the start. And that is horsepower, which is the rate at which work is done, and then the watt, which is really, if you are into resistors at all, and especially the dynamic side of it, the watt is where we rate our resistors. So where do these terms come from? It's, at least for me, it's a little bit interesting. The horsepower. So there was a pretty smart guy back in the late 18th century, James Watt, and while he didn't invent the steam engine, he perfected the steam engine and came up with some new changes to it. Now, what James wanted to do, though, he wanted to sell more of these steam engines. And what his idea was to convert what that horse could do to what his steam engine could do. So he came up with a calculation so that he could say, hey, my steam engine does this, which is the same as what your horse does, so that he could have the farmer say, okay, that makes sense. I'll pay you this much for that use of the steam engine versus having to pay for this horse. Now, for what we use, we go and take that horsepower, and as you can see, there's a lot of science and math that goes into it, but the bottom line is and there's a lot of guys smarter than me long time ago, converted that horsepower into a watt. And actually, I think it was James Watt that probably did it because his name is actually associated with it. So we come down and we find out that 1 horsepower is equal to the 746 watts. So we've got a couple different available powers. We've got the motor wattage, which is the horsepower, the drive horsepower, the motor horsepower, times 746. That's our motor wattage. That's the maximum amount of wattage the motor can put out. And then we also have a peak wattage, which is that motor wattage times a braking torque. And it can go anywhere between 100 to 150% typically. So what dynamic braking deals with is regeneration. So when that motor becomes a generator, so the load starts putting power back into the generator instead of the motor, instead of the motor putting power into the load, it's getting power back put into it. So what happens is if we don't deal with that, we start putting an overvoltage on the bus, and then the bus trips. So what we find out is probably more commonly than anything, when somebody gets a new VFD and a motor and they set it up, they start having problems with overvoltage trips. And a simple solution is putting a dynamic brake on the bus. So regeneration in a VFD, you can see what we're doing is we're bringing in 3-phase power into a rectifier and converting it to the DC bus, which then the inverter uses along with a control to put out a 3-phase pulse width modulation, which allows us to adjust the speed of the AC motor. Now, the downside of that system is you can see that we can't go back to the system with the rectifier. The rectifier says, no, I only go one way. I go onto the bus. It won't allow power to come off of the bus. So basically, an easy or simple way to think of this is the DC bus is a sink. Just like your kitchen sink, it basically absorbs this power, and this power starts filling up your sink. So what you could do is you could put a chopper on that sink at the top when it's starting to get overfilled, and it senses, hey, I'm getting too much power or too much water in the sink. Now what happens is it opens up a drain at the bottom. And as you can see, I've got 2 drains at the bottom that feed into the resistor. You've got a 1 ohm drain, and as you can see, the 1 ohm drain is a big drain, and it allows the voltage buildup to discharge very quickly into the resistor. So for a 1 ohm resistor, it's going to be a bigger resistor on the same bus as a 100 ohm resistor. And the 100 ohm resistor, you can see, is just basically, it's smaller. It's going to get less of the overvoltage off of the DC bus. It's going to drain the sink a little bit slower, so you could require a smaller resistor. But the bottom line is, typically you're going to be at the low end of the scale. You're going to want to get most of the power off of the bus, most of the overvoltage drained off that bus as quickly as possible. So all we're doing again is we're taking a chopper, which is basically that little switch that says, hey, I've got an overvoltage occurring. It takes that power off the DC bus, puts it into the dynamic brake, and that dynamic brake gets rid of that energy in the form of heat.
It's a good time for a poll question, Joe.
Sure.
Give everybody about 20 seconds to finish voting. Okay, we've got about 80% voted, so I'm going to close the poll.
So there are the results.
Okay, go ahead, Joe.
Okay, so now getting back to it, you'll see when you go to a lot of the sizing sites or sizing pages for the VFDs, they'll have braking versus overhauling load. So typically, all you're talking about, is, as you can read, is braking. You're bringing that load to a stop, and an overhauling load means you're trying to maintain a constant speed. So for dynamic braking, all we're talking about is a power over time. And what we do is we can calculate the area under that triangle, and that will give us the power required. Now, if we take a look at the overhauling load, that same power over the same amount of time is double. We take that area, it's now, instead of that taking the area under the triangle, we're taking that full area, which is this rectangle. And that's why if you ever go to the charts, you'll see that typically the size for an overhauling load at the same duty cycle is going to be double of a braking load. And that's the reason behind that. And typically when you're looking at these cycles and they start talking about 10% or 50%, their cycle is usually over a minute. That can change, and it probably can vary from manufacturer to manufacturer, but what I've seen, and typically what we see a lot of, when I talk to a lot of our inside sales guys, typically the cycling is based upon a minute. So if it's 50% duty cycle, you're talking about this thing being on 50%, either overhauling or braking, and then being off 30 seconds to complete the 1 minute cycle. And we can always calculate different cycles. If you ever come across anything like this and it doesn't match up simply to that page that you're looking at, that's when you probably want to give us a call or send us an email, and we can help walk you through it. This is our inside sales guys. This is all they do all day long. And after a while, you get pretty good at it. So it takes some of the guesswork out of it for you, and it allows you to understand what you're doing, but you don't need to be the total expert on it. So again, what do you need to know? What you need to know in order to either size it yourself or, again, call us and we'll help you with it, you need to know the ohmic value. And the ohmic value is typically supplied, not typically, is supplied by the drive manufacturer. And what we do is we take that minimum ohmic value, multiply by 10%, and that would be the ohm that we would use, the ohmic value that we would use. And the reason being is, on all the resistors that we sell, it's a plus or minus 10%. It's a really rare occasion that you get to the minus, but you might be a little bit too far below the minimum if we're on the minus side of the ohmic value, and that might cause you some problems or issues. So build in the 10%, and that usually works fine. What's the motor that it's going on? And that would be if it's a 10 horsepower motor or 50 horsepower, anywhere in between or larger. Take that motor horsepower, multiply it by your 746, and there's our KW rating that we would need. And then we get back to what we just discussed, which is the braking or the overhauling, you'd need to know which one it is, if you do know, and you'd need to know the duty cycle, which would be that time on, time off. Now, I will say this, probably when it comes to resistors, unless you're getting into a 600 horsepower or 500 horsepower or some of the really large ones, you can never oversize a resistor. The only thing that could happen by oversizing the resistor or making it too big is that you will run cooler. Now, it's going to cost a little bit more money, but when you're at the smaller end, you're talking dollars. And when you're at the high end, you could be talking about hundreds and thousands of dollars. Maybe that's when you want to get and nail it. But keep in the back of your mind, the smaller the resistor gets, the dollars don't come into play as much, and oversizing, again, will not hurt. So then we get into whether you're going to have this sitting indoor or outdoor. And then there's a host of other things that come under there, whether you need UL or CSA or some other things. But these are the basic things that you need for either yourself to size this, or, again, we can size it for you and help you out on that. So just as a quick summary, all we're doing is we're taking the overvoltage off of the DC bus. We're converting that overvoltage from energy into heat. And you have to keep in the back of your mind that I haven't mentioned this yet until the very end here. The temperature rise over ambient of the hottest portion of the resistor gets up to 375 degrees C. So you have to keep that in the back of your mind of where am I going to place this thing. So if it's going inside of some type of panel or box, keep that in the back of your mind. This thing gets hot. A lot of times this is either mounted outside or maybe on top of something. So the post-Glover advantage that we see for us, if you call us or if you send us an email and it's not a hugely sophisticated, there's always the exception to the rule, but 99.9% of the quote requests that we get out in 24 hours. You're going to find that we're extremely price competitive. You're going to find out that we can do UL, CSA, and any other option that you might come across that would apply to a resistor. And I think one of the huge advantages that we have is we have 2 to 3 day shipment on units under 10,000 kW as standard. And sometimes we can even ship them next day if you're really in a pinch. So that's it. It's that easy. If you have any questions, let us know. I guess put them into the chat and send them to Michael and he can share them with me. And I just want to thank you all for your time. That's all we've got for you. And again, keep us in mind. You don't need to be the expert on dynamic braking. We certainly would love to help you out.
Okay, we're going to have a couple polls here and hopefully a couple questions from you guys. And here's some other topics that post-Glover could present on, and we'd love to have your input on that. We have a question from one of the audience. Does the resistor bank need to be cooled? Why don't you take that one, Joe?
Okay, well, it depends upon the size of the unit. Most resistors that you'll run across typically are convection cooled. So they need to have space around them so that they can, basically it works like the chimney effect. It's going to pull cool air into the bottom. That cool air flows through the resistor and comes out the top in the form of hot air. And honestly, that's sort of the science that goes into the resistor, is you have to make sure that you have enough element, enough surface area of element, and enough opening at the bottom and enough opening at the top to make sure that you're getting enough air to flow through the unit. And based upon experience, years of experience, and we also have a test lab that we've actually proved out our experience, because NEMA says the temperature rise of a resistor, if you follow their rules, is 375 degrees C over ambient. And if you go with the UL rules, they're a little bit different, but it's a temperature rise is pretty close. Their temperature rise is 375 degrees C over ambient. So the bottom line is, like, 375 is that magic number to remember of them getting hot, and that's the number that we have to hit when we design our units.
Joe, can I add something to that? People need to realize that in dynamic braking, we're just having it on when that motor is acting like a generator. So it may be 5 seconds, it may be 10 seconds. It's not like that. Resistor typically stays on for 5 or 10 minutes. So that's why you really aren't concerned. The resistor gets hot, but hopefully the enclosure will never see that kind of external temperature.
Well, the enclosure itself is there'll be a sign on there that's it's warm to the touch, it's hot to the touch, but the enclosure only gets to, a lot of times you're probably looking at maybe 125 degrees C, which is hot, and I wouldn't want to sit on it. But the enclosure temperature versus the temperature rise of the hottest points of the element are, you can see, two drastically different temperatures. Once it starts coming off of the element, it starts to cool fairly quickly, and the distance between the top of the element versus where the top of the resistor enclosure is, that temperature difference is, like I said, it's quite different, but you're probably looking about 125 degrees Fahrenheit, not Celsius. For some reason we do it differently. So the exhaust temperature and the temperature of the enclosure is in Fahrenheit. I don't know why they do it this way. And the element rise is in Celsius.
Okay, great. We have some great questions coming here. Thank you, audience, so much. Here's a good question. If overvoltage is a problem for the drives, why aren't the braking resistors included in the design of the drive? And I'm going to take that one and get your comments, Joe.
Sure.
I think one of the main reasons is going to be because there are many applications for variable frequency drives where the overvoltage of the DC bus will never be a problem. There'll never be a need to apply braking to the drive. There will never be a situation where the load is regenerating voltage onto the DC bus. One example would be a pump application. Many times when a VFD is applied to a pump, as soon as that motor stops, the water does not continue running, and almost immediately the motor slows down. And an opposite example would be a high inertia saw blade in a paper or pulp mill, where that saw blade is so heavy and has so much inertia that it will just keep spinning and spinning and spinning, all the while generating voltage onto the DC bus, and will at some point kill the drive.
Michael, I'd like to add to that. There are some drives out there that do have a 10% braking resistor built into the drive. So you need to look at the specific drive. Some do have some dynamic braking built into them.
Yes, that is absolutely correct.
Thank you.
Okay, this one I'm not going to be able to answer. What parameters need to be changed in the Allen Bradley PowerFlex 525 VFDs when installing resistors? can't comment on that one. Okay, here's a good one for Joe. Would you mind explaining the overhauling function? Is this a situation where the load drops during operation and the motor has to be slowed down?
It's a little bit difficult sometimes to come up with great applications because a lot of times both are part of the application. But say there's a large coal conveyor, and it comes out of the mine and it goes over, and then it goes down a little bit and it goes over to a far part of the mine site, and they want that conveyor to go at X number of feet per second. And depending upon what's loaded on that conveyor and whether that conveyor is going up or down, most of the time, the motor should be putting power into that conveyor to move that load. But every once in a while, maybe that load is going down and it causes a quick regen where it's putting that inertia from the conveyor movement back into the load, back into the motor. That's an overhauling load. So it's trying to maintain a constant speed of something along the lines of, say, in my mind, that's probably the easiest one to understand, but a large conveyor or that type of application. Does that make sense?
Okay, here's a good question. Are there any special considerations required for sizing or specifying the conductors that feed the resistors? It's a DC.
That one
are you talking about high temp wire? Are you really looking for high temp wire inside the resistor itself, or feeding coming from the drive to the resistor bank?
I think he's asking about from the drive to the resistor bank. And that would be a DC load, correct?
Yes, it's a DC load. Probably the best thing to do is just size it to the full load current that's going through the resistor. Once you know the voltage of the drive, the DC bus, and you know what the resistance is, so you can calculate a current.
Right, and it depends on the drive. You're going to have to look in the owner's manual, but for a 480 volt drive, I believe on a Danfoss drive, the DC voltage is 690 volts. So you need to make sure you use cable rated for at least that voltage. Okay, here's a good question. Based on the graphic that indicates the braking resistor is directly connected to the DC bus, how are resistors added to the drive DC bus without violating the UL listing of the drive? Well, the resistor is a external component to the drive. When drives
connected
go
through the chopper, by the way, just if that's not clear. The chopper is the on-off. The IGBT is the chopper, and that's connected, and then the resistor is connected through that. But I guess it's still, I guess it would be the same question. I couldn't tell you how it doesn't lose or how it gets a UL listing, but I do know that it's done all the time. And I know that our units can be UL listed, and I believe that most of the choppers that I've seen out there are UL listed.
And the chopper may be in the drive, or the chopper may need something you have to
do. Most of the time, I believe the chopper, for the ones like most of the smaller Rockwells, yeah, it's in the drive. So it's already there to accept a resistor.
In the bigger ones, it may be external.
Correct.
There's one question, Michael, I'd like to address. Somebody said, in your experience, what would the duty cycle for an 800 kW drawworks drive of a land drilling rig be? One thing Joe did not mention in his slide is there's actually what's called a NEMA resistor application table. And it goes into all kind of different applications, from paper mills to pipe work to power plants to cranes, flour mills, coal and bridges, coal mines, and they have different resistor class numbers. So if you need that, we can send you that list. When you submit it to Post Glover to size it up, you can just say, hey, this is for a calendar on a paper mill. And we're going to know that's resistor class 154. And so we can actually size.
In reference to the 800 kW question, it sounds like somebody who deals with Houston quite a bit, and especially obviously since they mentioned rigs. So we've got a lot of different customers in Houston, and they all have a little bit of a different idea on how the rig works. A lot of them are changing. The original spec was 1200 kilowatts continuous, period. And a lot of them are starting to reevaluate what the rig actually is requiring. And some of them have gone down to 900 kW continuous, and some of them have gone down to 900 kW to 800 kW with a duty cycle. And there is no standard duty cycle, but anywhere between 15 and 30 seconds on, and so that would be out of a minute. So you're looking at 30 seconds on, 30 seconds off, or 15 on, 45 off, and it allows you to, now, in a unit that size, 800 kW, that's when you really want to hit the frog hair when it comes to fine-tuning the resistor, because making sure that you're sizing the unit properly will allow you to potentially save some money, and making sure that it hits exactly what you want it to do with that, the magic number, which is the 375 degree rise in temperature. So if you have any questions on the 800 kW, you might want to send me an email. If you could get that from John and Michael, and we could work with you to try to maybe fine tune your 800 kW unit for you.
There's one question we missed, Michael. Somebody asked, do we have similar presentations on sizing neutral grounding resistors? And yes, we actually have a whole presentation on that. There's a web version actually on our website, but if y'all would like us to do it again, I'm sure we could present that again.
There's one more question. Is there a motor horsepower minimum for which braking resistors are required? It's a great question.
Well, the smallest units that we get into, we have I think just a little bit under 300 watts, which, as you can see, is a small unit, but I think it depends upon the manufacturer of the motor. Some motors can absorb a little bit of regen, and depending on how much regen we're talking about. So it really depends upon the VFD guys of whether they recommend if it's required. But it can go down to just a small horsepower motor, half horsepower. So I guess it really is more, what's the DFD guy saying that you're going to need, and what's the application? Is it seeing that it's actually dumping a lot of energy every once in a while back onto the system that you need to dissipate?
That's great, Joe. Thank you so much for your time, and thank you so much for the participants for paying attention and asking questions.
All right. Well, thank you. I'm going to get off now. L3, thank you so much, Michael and John, and everybody that listened in. And if you have any questions, that I didn't answer, get a hold of these guys at L3, and I will work with them to get anything answered that I didn't, that I left a little bit open or vague, and any other jobs as far as quotes that are required, send it to them, and we'll get them taken care of for you. And again, thank you.
Thanks again, Joe.